Okay, very good morning, one and all. Today we can start up with the differential pulse code modulation system. Okay, so in the last class we have seen the main drawback of the PCM system, and we have undergone through the SNR evaluation of uniform quantizer, and we have seen the main drawback of uniform quantization. Uh, that is, its SNR is not stable value. Okay, so in order to provide a stable SNR, we are opting differential, what is it? Non-uniform quantization. We use non-uniform quantization, and compounding is a process of non-uniform quantization where you can provide a stable SNR. Okay, you can provide stable SNR by using compressor, next followed by uniform quantization, and then followed by expanding at the receiver. So the process of compression and expanding at the receiver is generally called as compounding. This type of system will provide a uniform SNR or stable SNR. So what is the importance of compressor? Compressor will it will do, it will amplify the low magnitude input and attenuate the high magnitude data, and the expander will so that what this compressor will do, compressor will generate a uniform magnitude message signal that will be applied to the uniform quantizer, and the uniform quantizer output will be a uniform data, okay, uniform amplitude, uniform discrete levels of amplitude, and that is fed to the encoding and then to the transmit channel. Okay, so thereby you can provide like constant SNR, but at the receiver you need to regain the original magnitudes of message signal. So that's why what we'll do, we'll make use of expanding at the receiver in order to obey or in order to get the inverse action of compression, so that you can regain the original form of message signal. Okay, so by using expanding, what this expander will do, it will attenuate the low magnitude and amplify the high magnitude input signal. Okay, so this is how the compressor can be able to compressor as well as the expander, compressor at the transmitter and expander at the receiver can be able to maintain stable SNR for the PCM system. So till now we studied the pulse code, all the types, all the elements of PCM, and uniform and non-uniform quantization, everything we studied. But now let us go through some drawbacks of PCM system. We have some sort of drawbacks for a pulse code modulated system. Okay, so the main drawback of this is it will transmit all the number of bits per sample. Normally for a particular sample we are encoding as some n number of bits. Okay, so how many bits is each and every sample constitute? Each and every sample consists of n number of bits. Okay, so in the general traditional PCM system will transmit all the number of bits present per sample. For example, in particular sample 3 bits are there. Okay, you are representing the amplitude levels as 2 power n number of levels, thereby you can encode it as n bits per sample. For example, if the n value is 3, and in PCM, in the general traditional PCM, what we'll do, we'll transmit all the number of n number of bits per sample. Okay, so what happens to the value of n? N will be higher value. So n multiplied by fs, sampling frequency, gives you the information rate or signaling rate. So already we defined signaling rate as the product of n and fs, where n is the number of bits transmitted per sample and fs is the sampling frequency. Okay, so but what happens to the signaling rate then? Signaling rate will get increased because we have some value of n, higher value of n, and we are transmitting all the number of bits. And what happens to the bandwidth then? Bandwidth will also increase because bandwidth is half that of the signaling rate. Once if we transmit all the number of bits per sample, even we have some sort of redundancy. Okay, we can see the problem in the next slide. So to overcome that kind of problem, we are using differential PCM system. Okay, So let us move to the next slide so that it will be more clear, so that we can see the main drawbacks of PCM, traditional PCM, and we can see how this differential PCM overcomes the problem of traditional PCM. So that is the learning outcome of the module 6, which is differential PCM. So we have PCM system, and why we are going to opt differential PCM, and what is the basic difference between differential PCM and traditional PCM. Okay, let us see the advantages of PCM. So we know PCM has a lot of advantages. So what are the advantages? In terms of noise and interference, this PCM system has high immunity, and even it is highly robust. Okay, so it can be able to eliminate the noise and interference that occur in the PCM system, because already we discussed it has source and channel encoding system and repeaters in the channel. So these repeaters will eliminate the noise and the distortion. Okay, and similarly we have in the channel encoding systems, because of the channel encoder, what it will do, it will detect and correct the error bits. Okay, like that PCM has lot of advantages. The first advantage is it is highly robust to noise and interference, because of the presence of channel encoder as well as repeaters in the channel. Okay, so it is highly robust to noise and interference. So second advantage is it has good regeneration. Okay, because in the channel we have regenerative repeaters are there, which will regenerate every time the original form of PCM signal by eliminating the noise. Okay, so next third advantage is it's efficient. It is highly efficient in terms of providing a trade-off between SNR and bandwidth. So we are saying that this PCM uses high bandwidth because it transmits all the number of bits present in the sample. If there are n number of bits per sample, this PCM will transmit all the n number of bits for a particular sample, so that how many samples are there? So more n number of samples, where n ranges from minus infinite to plus infinite. Okay, so many number of samples are there, and each and every sample we have certain number of bits. All the bits for a particular sample will be transmitted in the case of PCM. So that's why we need to provide a trade-off between SNR and bandwidth. That SNR bandwidth trade-off is very efficient in the case of PCM. Okay, and it provides uniform format. Even in the case of non-uniform quantizer, we are using uniform quantization in between compressor and expanding. Okay, next, this PCM system, please observe fifth advantage. This PCM system, traditional PCM, has a flexibility in adding and dropping the channels. So you can easily add as well as drop the channels intermediate during the channel. Okay, during the transmission, you can easily add and drop channels. And last advantage is it's highly secure. It is highly secure because you are encoding it into a secure data. So that's why you because of your good source encoding techniques, you can provide good security to the PCM, that is data sequence. PCM signal is nothing but the data sequence. Okay, so that's why the data is highly secure, so that strangers cannot capture the data. So these are all the advantages, but the one and only drawback of PCM is, let us go to the next slide. So the only drawback of PCM is that it needs large bandwidth. It needs large bandwidth compared to the analog system. Okay, PCM system needs large amount of bandwidth. PCM system needs large amount of bandwidth compared to the analog system, as it transmits all the redundant bits. So what this PCM will do? The PCM will transmit all the number of bits present in a sample. So it don't remove the redundant data. So it do not remove the redundant data and it transmits all the bits per sample. It transmits all the bits present in each and every sample. So what happens to the value of number of bits as and when the number of bits increases? We know that our signaling rate will increase and at the same time the bandwidth will also increase, because there exists a relation between the bandwidth and signaling rate as R by 2. Bandwidth is equal to half that of the signaling rate. So as and when the signaling rate increases is more, our bandwidth will also increase. So PCM requires large bandwidth compared to the analog system. Okay. So how can you overcome this drawback? By using differential PCM. What this differential PCM will do? This differential PCM reduces the number of bits per sample. It reduces the transmission of number of bits per sample. Okay. So once you reduce the number of bits per sample, n will reduce. As n reduces, because signaling rate is equal to n into fs, as n reduces, r will reduce, and as the signaling rate reduces, our bandwidth will also reduce, because bandwidth is equal to half that of the signaling rate. So that is the main drawback of PCM system. So what is the drawback of PCM system? PCM system needs large amount of transmission bandwidth. Okay. So in order to overcome this, our DPCM, what it will do? It will remove the redundant data. It will remove the redundant data by making use of prediction filter. Okay. So it transmits only the difference data bit. Difference between the sample values is transmitted. Not all the bits present in the sample. Okay. So this is about the first point, that is PCM needs large bandwidth. In DPCM we can reduce the required amount of bandwidth for signal transmission. Next, and one more drawback is also there, that is its encoding process as well as decoding process as well as the quantization process of PCM is somewhat complex. Okay, so DPCM circuitry is complex. And how can you overcome that? PCM circuit is complex. So how can you overcome that problem? By using DPCM circuit, which reduces the complexity that has been provided in the case of PCM. So DPCM circuit reduces the complexity that has arrived in the case of PCM. Okay. So next, if you observe the third drawback, that is occurrence of quantization error. See, already we discussed so many times the presence of quantization error in the traditional PCM. So we have defined it as some error E, and we have evaluated the noise power, and because of that quantization. So how can you define error? Error is the magnitude is delta by 2. It is plus delta by 2 in the positive extremity, and in the negative axis it is minus delta by 2. Okay. So we have lot of quantization error in the case of traditional PCM. Now that error can be you can reduce that error by making use of prediction filter in DPCM circuit. In DPCM circuit, you are using prediction filter. That prediction filter will reduce the quantization error, okay, that occur in the case of PCM. Okay, these are the three drawbacks of traditional PCM, and even we have observed how can we overcome by using the differential PCM. Okay, so here black wording represents the drawback of PCM, and red color data represents the importance of DPCM, and how the DPCM will overcome the corresponding drawback shown in the red color data, shown in the black color data. Okay, so red represents the DPCM data and black one is a PCM data. So three drawbacks. Okay, so one of the drawback is PCM requires large bandwidth because it transmits all the bits present in the sample. But what this DPCM will do, how can it overcome that problem? DPCM reduces the bandwidth by transmitting only the difference between the sample. Okay, not all the data bits. the difference data bit between the two sample code words is transmitted, not all the bits present in the sample. Thereby the value of n will reduce, so our signaling rate will reduce because r equals to n into fs. So as and when signaling rate reduces, what happens to the bandwidth? It also reduces because bandwidth is r by 2. So what is the second drawback? The circuit of PCM is complex, so we can overcome the problem by using DPCM circuit. We can reduce the complexity by using DPCM circuit. And third drawback is occurrence of quantization error. This quantization error is also called as round-off error. Because we are transmitting all the bits present in the sample, it generates some deviation from output to the input. Okay, so the difference between the output and input is, we defined it as quantization error. That's nothing but the round-off error. Okay, how can you overcome that using DPCM circuit? By using prediction filter. Okay, if you observe the DPCM circuit, you can identify prediction filter in the circuit. Okay, this is about the three drawbacks of traditional PCM, and how can you overcome that drawback. And before going to the next slide, please observe the graph shown on the right side. So please observe the graph shown in the right side. If you observe that graph, x-axis, take x-axis is the input of the quantizer, or you can define it as a sample data. So input of the quantizer is a sample data. Okay, and what are the sampling intervals? TS, 2TS, 3TS, 4TS, up to 10TS we considered. Okay, we consider 10 sample data. And now, please observe the y-axis. What is y-axis? Quantizer output. Okay, so what is quantizer output? XQ of NTS. And always please remember that the quantizer output is the discrete amplitude sample. So that's why you will have discrete amplitudes in the shown in the y-axis. If you observe the y-axis, you can identify that it is a 3-bit data. It is a 3-bit data. So mean how many number of amplitude levels should be there? 2 power 3. It means that 8 number of amplitude levels that range from 0 to 7. We already represented the encode form of, or the code format of all the amplitude levels in the brackets. In the brackets you can identify the code representation or encoded form of the corresponding amplitudes or the corresponding voltages. Now, please observe the at TS, sampling interval TS. At TS, what is the magnitude of message signal? Any one of you please respond. What is the magnitude of TS? Magnitude of message signal at time interval TS? Any one of you please respond. It is 2. Yes, it is equals to 2. So what is the code representation? 0, 1, 0. Okay. Next, at 2TS, what is the magnitude? 4. So 4 is represented as encoded form as 100. Okay. Next, at 3TS, it is 5, nearer to 5. So we represented 5. So 101. Next, similarly at 4TS, it is the magnitude is nearer to 6. So we represented it as the encoded form is 110. Similarly, at 4TS, 5TS and 6TS, you have a magnitude of 6 because analog signal is a continuous varying signal and its magnitudes gradually, there will be a gradual change in the magnitude, not an abrupt change as in the case of digital signal. In the case of digital signal, the magnitude abruptly changes from 0 to 1 or from 1 to 0. But here, because the message signal is a continuous signal, its amplitude gradually changes or instantaneously changes. From instant to instant, it gradually differs. There will not be a drastic change. Okay, so that's why at 4TS, 5TS and 6TS, see, I represented some 3 points down to the graph. Please observe the first point. Please observe the magnitudes of sampled information at 4TS, 5TS and 6TS. If you observe the magnitudes at 4TS, 5TS and 6TS, what are the magnitude? What is the magnitude? It is 6. It is directly equal to 6. So the magnitude is same for all the 3 sampling intervals. Now what this PCM will do? PCM will transmit these type of redundant information. For all the sampling intervals, the magnitude is 110. Okay, this PCM will transmit these type of redundant data bits for all the samples throughout the system. Okay. Now, if you observe the data at 7TS, 8TS and 9TS, if you observe the data at 7TS, 8TS and 9TS, almost all the magnitude is 101. Almost all the magnitude is nearer to 101. Here also the signal will transmit the redundant data. Here also the signal will transmit the redundant data. Which system? PCM system will transmit this 101 thrice. So 3 times it will transmit 101. Mean that you are transmitting the redundant information thrice. Okay. And at 4TS, 5TS, 6TS, you are thrice transmitting the redundant data. And even at 7TS, 8TS and 9TS, you have a data of same data. So this same amount of information, or you can say the redundant information, is transmitted by PCM system thrice. Now, please observe the third point, that is at samples 9TS and 10TS, if you observe, please observe the magnitudes at 9TS and 10TS. At 9TS the magnitude is 101 and at 10TS the magnitude is 100. At 10TS the magnitude is 100. If you observe the magnitudes at 9TS and 10TS, if you observe the magnitudes at 9TS and 10TS, there is only 1 bit difference. Okay, so because the first 2 from the LSB bit, if you observe the LSB bit of those 2, you will have that bit difference. Okay, so you will have only 1 LSB bit difference, because for 9TS you will have 101 and for 10TS you will have 100. The difference is only 1 bit. Okay, so instead of transmitting this 101 and 100, you can transmit only the difference bit. Okay, the difference bit there is 1. So if the difference bit is transmitted, that is enough. But what this PCM is doing, PCM is transmitting all the number of bits transmitted per sample. So it transmits all the bits present in the sequence. Instead of taking the difference, it will transmit all the redundant information. So what this DPCM will do? This DPCM will take the difference between, 2 successive sampled information. It will take the difference between 2 successive sampled information, and if there exists any difference, the difference data bit is transmitted. Otherwise, it won't transmit any data. Okay. So is this slide okay to everyone? Can we move further? This is very important. So drawbacks of PCM. Okay, what is the first drawback? It needs large bandwidth because it transmits all the bits, all the redundant bits present in each and every sample. Second drawback is circuit is complex. Third drawback is it possesses quantization error. It is also called as round off error. Okay, why it is called as round off error? Because the amplitude, by using quantizer, you can round off the amplitude to a nearer magnitude. Because if the first sample, if you observe, it is nearer to 2. So you are rounding off to 2, rounding off the amplitude to 2. So that's why the error created by the quantization is also called as round off error. So So while representing DPCM or while explaining DPCM, you should explain this graph, because in PCM you are transmitting all the bits present in each and every sample, mean that it is transmitting redundant amount of information. This information you can this redundant information you can deduce, and you can transmit only the difference bit. Okay, that's we can do using DPCM. Is this okay to everyone? Can we move further? Now, what this is the principle of DPCM. What this DPCM will do? So, instead of converting analog to digital directly, what this will do? Here, the analog signal is sampled, as in the case of PCM, and the difference between the actual sample value and the predicted value is collected, and the difference bit will be quantized. Instead of quantizing all the encoded all the bits present in each and every sample, only the difference data bit is collected, and that is quantized. Okay, and that whole sequence will be transmitted. Okay, instead of transmitting all the number of bits present in each and every sample, only the difference data bit between each and every sample will be transmitted. Okay, so DPCM, please observe second point. DPCM code words represent the differences between samples, but in the case of PCM, code words represent the sample value. So we defined code word there. Code word is a combination of the bits present in each and every sample. Okay, but what these DPCM code words represent? It represents the differences between the sample values, not the bits, not all the bits present in each and every sample. Okay, so DPCM code words represent the differences between the sample values. So that's why it is called as differential PCM. So because you are taking only the difference between the sample, this is called as differential PCM system. Okay, why this PCM system is called as differential PCM system? Because here the code words represent the difference between each and every sample value. Now, let us please observe the DPCM transmitter section. So this is the DPCM transmitter. So this is the DPCM transmitter. What you are doing here? So here you have sampler and encoder as usual, but the coming to the quantization, here you are going to reduce the quantization error. How can you reduce the quantization error? By reducing the number of bits transmitted. So by reducing the number of transmitted bits, you can reduce the quantization error. Now, how can we reduce the number of transmitted bits? For example, please observe the transmitter circuit. Let X of NTS. What is X of NTS? Is a sample signal. Please take the input signal to the quantizer as X of NTS. Now, for example, this X of NTS possesses a data of 101. Let us suppose take this at 5 TS. Now at 4 TS, what is the magnitude? Already we observed the graph, and it is also equal to 101. It is also equal to 101. Now every time the sampled signal is compared with the past value. Okay, so here you can observe predicted signal. The predicted signal is nothing but the past sample data. So what is predicted signal? X cap is nothing but the expected value. It is nothing but the expected value. Okay, this is nothing but the past sample data. Past sample data is the predicted signal. Okay, so present sample data is every time this will be compared with the past sample data, and the difference will be applied to the quantizer. Now what is the difference between 4 TS and 5 TS? 0, because that is 101, and present sample data 5 TS is also 101. So the difference is 0. So no bit will be fed to the quantizer whenever present sample data is equal to the past sample data. Okay, here past sample value is defined as a predicted signal, because here you are making use of prediction filter. You are going to predict the data. How can you predict the present data? You can predict the present data by comparing the past data with the present existing sample value. So the newly arrived 5TS sample value is compared with the past data. Every time the present sample data will be compared with the past sample value, and the difference will be generated, and that difference is called as error. Okay, and the difference is provided by the comparator. So what this comparator will do? Comparator will take the difference between the sample signal and predicted signal. Okay, so x of NTS minus x cap of NTS, that is nothing but the error E of NTS. The same thing we represented in the equation 1. So what is comparator output? Comparator output is error signal, or the difference between the sample signal and predicted signal. Difference between the sample signal and predicted signal is the output of comparator. It is defined as error E of NTS, that you can identify from the equation 1. So equation 1 is E of NTS is equal to x of NTS minus x cap of NTS, where x of NTS is sample signal and x cap of NTS is predicted signal. Take that as equation 1. Now, let us move to the quantizer section. So what is the input to the quantizer? The difference between the sample signal and predicted signal, which is nothing but the E of NTS. That acts as that error signal acts as input to the quantizer. So here we are not transmitting the sample signal directly to the quantizer, as in the case of PCM. What we are doing here? We are taking the difference between the sample signal and predicted signal, and that is transmitted, that is applied to the quantizer. Now this quantizer will generate the output signal. Okay, that output signal is the sum of the input and some error provided in the quantizer. Let that error provided by the quantizer or inherited by the quantizer be Q of NTS, that is quantization error. So what is the total output signal EQ of NTS? Quantizer output, that is also error, because it is a sum of the difference bit and the quantization error or induced quantization error. Okay, so E of NTS plus Q of NTS is equal to EQ of NTS, where EQ of NTS is the quantizer output signal. The same thing we represented in the equation 2. So what is the quantized error output? So quantized error output EQ of NTS is equal to E of NTS plus Q of NTS, where E of NTS is the error signal and Q of NTS is the quantized error, Okay, so you can observe EQ of NTS as quantized output. The same we represented in equation 2. Now, so that is about the so what is the difference between the quantizer section used in the DPCM and PCM? In PCM, directly the sample signal is applied to the quantizer, but in the case of DPCM, the difference between the present sample value and the past predicted signal, that is nothing but the past sample value, the difference is applied to the quantizer, not directly the sample signal. Okay, so you can reduce the redundant information by using this comparator. Now the difference data bit is applied to the quantizer. So what is the output of quantizer? But even with the difference data bit, this quantizer will inherit some sort of error. Let that quantizer error be Q of NTS, shown in the equation 2. So now the total output of the quantizer is the sum of the error E of NTS input, that is E of NTS, and Q of NTS, that is a quantization error, that is EQ of NTS. Now take that as equation 2. Now what is prediction filter? Here you are using in the feedback section, Okay, some sample of the quantizer output is applied as negative feedback to the comparator. So what is that filter known called as? This filter is defined as a prediction filter. Okay, it will predict the, or it will generate the difference between the sample signal and the past sample value. Present sample data is compared with the past sample value. The past sample value is defined as the predicted signal. Okay, so what is the input to the prediction filter? Please observe the input to the prediction filter. Some sample of quantized output signal, that is EQ of NTS, is added with the past sample data, that is X cap of NTS, and the sum of those two acts as input to the prediction filter, that is nothing but XQ of NTS. Let the prediction filter input be X suffix Q of NTS, where XQ of NTS is nothing but the sum of quantizer output signal, that is EQ of NTS, and the past sample value, that is nothing but X cap of NTS. The sum gives you the XQ of NTS. For the first sample data, you don't have past sample value. So past prediction value is 0 here for the first sample value. For example, first sample value occurs at TS. Then do you have any past sample value? No. So that's why here past sample value or past prediction value is 0 at the first sample instant. So directly the prediction filter input XQ of NTS is equal to EQ of NTS when we have no past sample value. When we have no past sample data, directly the quantizer output, the present quantizer output data acts as input to the prediction filter. Now prediction filter generates, the output equal to the X cap of NTS. So what is the importance of prediction filter here? Prediction filter stores the past sample data. Prediction filter stores the past sample data. Okay. Now let us take that equation as 3. What is the equation 3? Prediction filter input, that is XQ of NTS, which is equal to X cap of NTS plus EQ of NTS. If we have no past sample data, X cap of NTS will be 0. That occurs only at one particular instant. And for all the next successive sampling intervals, X cap of NTS, that is nothing but a past sample data will exist. Okay. So now please replace equation 2 in equation 3. Replace equation 2 in equation 3, because from equation 2 you will get quantizer output, that is EQ of NTS. Replace equation 2, that is EQ of NTS, as E of NTS plus Q of NTS in equation 3. Now, upon replacing equation 2 in equation 3, you can get XQ of NTS, that is the prediction filter input, as X cap of NTS, that is sample data, plus error signal, that is the comparator output, plus quantization error, Q of NTS. So take this equation as 4. So I think this circuit is clear to all of you. Okay, let us move to the next slide so that you can observe. So I have rewritten once again equation 4. So what is equation 4? The quantizer prediction filter input is equals to past sample data plus what is E of NTS? Comparator output, and Q of NTS is the quantization error. So take this as equation 4. Now how can you rewrite equation 1? Actually what is equation 1? Comparator output, that is error signal E of NTS or the difference signal. You can write it, it is defined as the present sample data, that is X of NTS, minus past sample data, that is X cap of NTS. Please rearrange this equation to get the present sample value, because you are going to predict that. So please get the present sample data. So how can you rewrite this? You can take X cap of minus X cap of NTS to the left hand side, so that you will get E of NTS plus X cap of NTS is equal to present sample data, that is x of NTS. Now you can replace x of NTS. Now you got x of NTS. Now you got x of NTS as E of NTS plus x cap of NTS. So from this equation 5, we can say that this is the prediction filter characteristics. What it is doing? You are going to predict the present sample data, that is x of NTS, by using past sample data, that is x cap of NTS. You are going to predict that. So that's why the filter used in the feedback section is called as prediction filter. So from equation 5, you can conclude that the filter used in the feedback is called as prediction filter, because you are going to predict the present sample value by using the past sample data, that is x cap of NTS. Now please replace the summation E of NTS plus x cap of NTS as x of NTS, that is, please substitute equation 5 in equation 4. So please replace the summation as x of NTS. Once you replace the summation as x of NTS, you can get the prediction filter input xq of NTS as x of NTS plus q of NTS. What is the prediction filter input? xq of NTS is equal to x of NTS plus q of NTS, where x of NTS is the present sample value and q is the quantization error. Now, what you can conclude from this equation 6? This equation 6 concludes that the quantization version of the signal, that is xq of NTS, that is nothing but the prediction filter input. Or you can say the quantized version of signal xq of NTS, it is independent of prediction filter characteristics. It is independent of past data prediction filter characteristics. It is directly equal to the sum of the present sample data and quantization error. So it means that even though you are adding prediction filter in the feedback section, the quantized version of the signal, that is xq of NTS, is independent of prediction filter characteristics, because from equation 6 you can see that the output of the quantizer is directly equal to the sum of present sample data and the quantization error inherited by the quantizer, but the output is independent of the prediction filter. So that's why even though you are adding prediction filter in the feedback section, it won't affect our PCM system, because the quantized output is directly the summation of present sample data and the quantization error. But this quantization error is due to the difference bit. Okay, and that's why we can conclude that this prediction filter characteristics does not affect our PCM system. So quantized output is directly the summation of present sample value and the quantization error, and you are going to remove the redundant bits by using the comparator. Okay, so the conclusion is that this prediction filter does not affect our PCM system, because from the equation 6, the quantizer output is directly the summation of present sample data and the quantization error. But here you are reducing the quantization error because you are reducing the number of bits transmitted. How many number of bits you are transmitting? Only the difference bits. So that's why you can reduce the quantization error, and you can by using the prediction filter. And one more thing is that prediction filter doesn't affect our PCM system. Okay, this is all about the PCM transmitter section. Now we can move to the PCM receiver section. If you observe the PCM receiver section, it consists of decoder followed by the prediction filter and then the low pass filter. Okay, so but in the PCM we'll have only decoder and low pass filter, but the transmitter section is simplified by reducing the quantization error. So the final intention is to reduce the quantization error here. Okay, so please observe the differential PCM receiver. In this DPCM receiver, we have decoder. So what this decoder will do? Decoder reconstructs okay, reconstructs the quantized version of the error signal, that is EQ of NTS. Decoder generates the quantized error signal, okay, that is EQ of NTS. From the incoming binary data, what is the DPCM signal? It is the binary sequence. That binary sequence is by eliminating the problem of redundancy. Okay, DPCM is also the binary sequence, but it don't consist of all the number of bits present in each and every sample. It consists of only the difference data bits. The difference data bit sequence is applied to the receiving section, and initially it is collected by the decoder. What this decoder will do? It takes that binary sequence and it will generate the quantized error signal EQ of NTS. EQ of NTS. Now that quantized error signal EQ of NTS is applied to the summer. Okay, this what this summer will do? Summer adds up the prediction filter data, because prediction filter stores the past sample data. The same prediction filter is used at the transmitter receiver section, okay, because it possesses all the past sample values. So prediction filter provides the past sample data. The past sample data is added with the quantized error signal. Quantized error component EQ of NTS. Okay, the decoder output is quantized error signal EQ of NTS. Now this EQ of NTS is added with the past sample data provided by the prediction filter. So the summer generates the quantized version. Summer generates the quantized version of original signal, because XQ of NTS is equal to EQ of NTS plus X cap of NTS. Already we studied the same equation at the transmitter section. Okay, so what is EQ of NTS? Quantized error signal is the output of decoder here, and the past sample value can be obtained by the prediction filter. Okay, the sum of these two gives you the quantized version of our original signal. Now up from this the PCM principle is same. So the quantized version is applied to the reconstruction filter. So this reconstruction filter generates the low frequency component, that is nothing but the message signal. So we have only one difference, that is the addition of prediction filter in the feedback section, in both the transmitter section as well as the receiving section. Okay, now let us move to the, so till now we studied the basic drawback of PCM and how can you overcome the drawback of PCM by using difference bit transmission, that is differential PCM, and we have seen the DPCM transmitter and receiver sections. Now I am going to keep the transmitter section and receiver section in a single slide, and I want to show you the principle behind that. Okay, this is the DPCM principle. Okay, so let us see the principle here. Here please observe the like encoding section. In the, this is the simplified form of the transmitter and receiver. So let us take the input sample bit as S and the predicted past sample data as S cap. Okay, and how can you define the prediction error? Prediction error is the output of the comparator, which is E, which is S minus S cap. So now all of the students, you can take like 101 as the input and 100 as the S cap, past data. The difference bit will be E. Okay, let the output be E is equal to 1, because let us take the present sample data as 101 and past sample data as 100. So what will be E? E is equal to 1 here. Only that data bit, that is the difference data bit, will be applied to the quantizer. Please observe the transmitter section, that is coder section. In the quantizer takes only the difference bit provided by this comparator. Okay, so comparator generates the difference between the present sample value and past sample value. So quantizer output will be, let the quantizer output is E cap. Okay, so E dash. So E dash and S cap summation will be S dash. So what is S dash? That is the prediction filter input. that is the sum of past sample data S cap and E dash, where E dash is the quantizer output. Okay. So S cap is equal to, which is the prediction filter input, and it is the sum of past sample data S cap and the quantized error component. So quantized error output, that is E dash, where E dash is equal to E plus Q, where Q is the, if you take quantization error Q, okay, and the error component as E plus Q is equal to E dash. So in the past slide, we represented it as EQ of NTS. So this is a simplified form. Okay. So what is the reconstruction principle? Already I defined you the reconstruction in the last slide. We represented the reconstruction formula or the receiving section. In the receiver, there we represented as XQ of NTS. Here it is the signal component. So S dash is equal to past sample data plus quantized error output, that is E dash. So that is the reconstruction principle. So what is the prediction principle? E is equal to S minus S cap, that is the prediction error. What is the reconstruction principle? S dash, that is a prediction filter input, is equals to quantized error output E dash plus S cap. Okay. So what is the reconstruction error? Error is nothing but the quantization error here. You can also call it as round off error. So what is Q? You can take it as S dash minus S, ante prediction filter data minus input sample data, or E dash minus E, quantization output minus quantization input. So that is the quantization error. So this is a simplified version of DPCM circuit. In general, in exams, if you get this question, you should write the transmitter and receiver section shown in the earlier slides only. This is a simplified form. Okay, so that you can easily remember what is error, what is reconstruction principle, what is quantization error, and how can you generate that quantization error. Okay, let us move to the next slide. Okay, I think from this module, each and every student can be able to see the importance of DPCM. How can you overcome the problem of PCM? What is the main drawback of PCM? It has large amount of bandwidth. It needs large amount of bandwidth, and a large quantization error is there. So to overcome that problems, we are using, and we are transmitting only the difference bit. If we transmit the difference bit, the quantization error you can reduce, and you can reduce the bandwidth. Okay, so like this we studied the DPCM transmitter section and receiving section. Okay, so any doubts in the today's session? I will post this PPT in your group. And one more thing is, I will post the modified module 4 in your WhatsApp group. Okay, because we have added one more problem in that. So that's why I will post you modified module 4, 5 and 6. In today I will post the 3 modules. Any doubts in the today's session, or can we close the session? Can we stop the class? See, one of you please respond. Is this DPCM okay to everyone?
Yes, ma'am.
Okay, thank you. So wait for 1 minute, I will take the attendance. Okay, ma, I took the attendance, and now you can leave the session.